In this video, we will continue our explanation for the origin of the solar system. So, the modern theory that kind of explains the origin of the solar system is called the solar nebular theory, or the proto-planet hypothesis. Okay, so let's take a look at what it says. So the first entry here says that the solar system was formed from a cloud of interstellar dust and gas particles. So obviously, in your grade 9, you learned about this interstellar dust and gas particles, meaning these are particles that are floating around in space in between stars. That's why interstellar. And these dust particles are, comes from supernova explosions in the past. But you have these clouds of dust particles, and in fact, we can search for some of them. So if I just search Nebula, I hope I won't get Nebula from the Avengers, but yeah, I get one. So these are, so if you look at this, those are towering clouds of dust. These are not stars. These are just dust particles that are in space. Obviously, they are very massive. They are not like the clouds that we see in the sky, but these clouds are, or nebula structures, are spans light years across. So again, in reality, when we look at it, it looks so dense. It looks so big, but when we actually go through space, these dust particles might be farther apart from each other. It's just that obviously from our perspective, again, it looks like that. But that is what the theory is saying. It's saying that solar system came from a cloud of dust. In other words, from a nebula. Okay, and according to the theory, um, the shock wave of a nearby supernova explosion compressed the cloud and caused it to rotate. Okay? The shock wave of a nearby supernova explosion compressed the cloud and caused it to rotate. So what does it mean? So it means that once upon a time, there was probably a floating nebula gas cloud of particles here. And then there was a supernova explosion here. And what happens is that supernova explosion, when it explodes, obviously it kind of creates a shock wave, a force that expands outwards. And when a force is exerted in an object, it does things to an object, right? So you learned this in grade 9. When you have an object, right, you exert a force on it, that object moves forward. But again, in science class, science is simplification of things. When we say an object, when a force is exerted on an object, when there's a net force on an object, and again, I don't want to study this in isolation, so I want to kind of mention as many related concepts as possible. But in grade 9, you learn that when you have net force, it results to an acceleration, right? Second law of motion. But there's more to that, because this one, you might think that, okay, there's an object, if there's a force exerted to it, it moves, so therefore it changes its velocity, meaning it accelerates. But again, that's a simplification, because in reality, we say that the object moves translationally if the force is directed to the center of mass, meaning the force is directed to the center of mass. But look at what happens when you have an object. Obviously, the center of mass is here. It's in the center. But if force were to hit it, but not on the center of mass, see, this is the center of mass here. So if I push it, it moves. But if force is exerted not on the center of mass, but somewhere here, guess what happens? Rotation. You don't get translational movement. You don't get translational acceleration, but you get angular acceleration, or in other words, we call rotation. Right? So you can imagine that this supernova, this gas cloud, and there's supernova here. When the supernova exploded, maybe some of the shock wave hit the side of that gas cloud, and that gas cloud started to rotate. Okay? And really, sir, how do we Do we really believe that that happened? So again, the thing is, we are not sure. We are not sure. But let me just point you to an article here. This is an article. This was August 2012, so maybe this has been updated. But exploding star may have sparked formation of our solar systems. You see, and if we look at the article closely, it says here, how do they know this? Well, because we used supercomputers to model the, see here you have a new 3D computer model to model the particles, because you have to remember that computers are powerful. Computers can program, so we know the laws of physics. We know that if an object is hit by a force like this, it moves like that, and in fact we can make very good simulations of reality from there. So, for example, just this morning I was playing billiards in my app in my phone, right? And billiards has a very and the game billiards has a very good physics engine about linear momentum, about conservation of momentum. When the cue ball hits another ball, how much momentum is transmitted to the other ball, and what angle would it move, and what angle will the cue ball move, and obviously that trajectory of this angle and that angle, if you calculate the momentum of this and momentum of that, they should be equal to the momentum of the cue ball before it hit, because momentum before is equal to momentum after. So what's my point? My point is math is very powerful. You can if you can program something accurately using the laws of physics, you can actually sort of make your own universe inside the computer. So what they did there was they created a 3D model of supernova somewhere here. Gas particle somewhere here, and a supernova adjacent to it, and then when the supernova explodes, they found a setup where, in some cases, the explosion of supernova would actually cause the nebula to rotate. So again, is that the same thing as a real setup, sir? Because after all, that's just a computer simulation. Well, we have a high degree of confidence that computer simulations uh, do emulate what happens in the real world, because guess what? Like designs of airplanes, designs of submarines, designs of things that move. Most of these things, they were not designed just from trial and error. They didn't just make a shape of an airplane and then, okay, let's find out if this flies well. No, they used computer models of how the wind flows, how the wind is distributed in the wings of the plane, and then kind of made deduct made make logical deductions of how the wing should be shaped so that it flows well before they made it into production. And the fact that we are successful at making airplanes, making other things, that means using computer models, using programs to kind of emulate reality is reliable. And so we have a degree of we have high degree of confidence that at least some computer simulation, some computer modeling actually works. And again, that's what they find out. They found out that if you have a gas cloud of dust particles, supernova explodes, hits it at the side, it causes rotation. Now, obviously, for some of you, you might be saying, but sir, you're saying that the origin of the solar system comes from the supernova. The question is, where did the the nebula come? There's nebula, gas cloud there. So where does the nebula come from? And again, remember, the topic here is just to discuss the origin of the solar system. We are not discussing the origin of the universe. So when we discuss the origin of the universe, you would know where this supernova, where these nebula dust particles came from. But for now, let's start with the supernova. Let's start with a nebula. I'm sorry, I'm always exchanging the term supernova and nebula. Nebula is a dust cloud, right? So again, there's a nebula there. supernova somewhere, it caused some rotation in the nebula. Now, some scientists disagree. Some scientists would say that no, when you have a nebula, dust clouds, they would eventually rotate even without the help of supernova explosion. But in terms of consensus, right? In terms of consensus, more scientists believe in this shockwave theory that caused the rotation of the nebula than those that don't believe it. But it's not definitive. It's not like a 95% 5% split. It's the split is very near, like 60-40. So it's not really definitive. But that's the point. Then what happens is the rotating gas flattened out over time, forming a protoplanetary disk. So when a gas cloud, remember this gas cloud is not flat. This gas cloud is three-dimensional. So you see a blob of gas, then it rotates in some rotation. And according to the theory, the rotating glass will flatten out over time, forming a protoplanetary disk. So because of the rotation, it will flatten out. So if it rotates like this, then the blob, which is three-dimensional, will flatten out like if the rotation is like this, then the blob will flatten out and will be like this. If the rotation is like that, then it will flatten out and be like this, right? So the fact is it flattens out. Now, again, why do we believe that this is so? I forgot that nam de diris ubos. Here, math predicts or proves that any rotating shapeless blob of particles would only preserve its rotational momentum and flatten out over time. So you see, when you have a three-dimensional thing here, three-dimensional, and it rotates in one direction, like it's in this slanting direction, over time, because of the collisions, what is only preserved is that rotational momentum. So if that rotational momentum is this, all of the motions that are against that plane, they will cancel out, because if you can imagine, if you have this particle and this particle hitting each other, they will kind of cancel each other's momentum. So the momentum along this and along that will cancel out, but the momentum along the rotation will not cancel out because they are not hitting each other, because they're moving in the same direction, remember? So what happens is that sphere would eventually flatten out over the direction of the rotation, right? So, and again, we can use kind of mathematical models to do that. So again, I'm sorry for spending a lot of time in explaining why we believe that this is true, because again, just going through this, just going through how the solar system is formed, it's useless if you don't know the narrative why we believe that these things are true. It's useless. It's not science. It's memorization, right? So forgive me if I really spend a lot of time on explaining why this is true. And in fact, if another proof for this is you can actually look at certain links from YouTube explaining this. So Minute Physics has a video about this, explaining why we have a three-dimensional blob of particles, why it would preserve its momentum and kind of flatten out over time. Okay, so I couldn't find the link, but well, that's not it. But search for it. It's called Minute Physics. So in Minute Physics, it tells you why would shapeless blobs of particles rotate and form and flatten out over time. Okay, so this is the video. Why is the solar system flat? And again, I will not play this for you, but you can search for it. So it just explains here mathematically how when you have a shapeless blob of particles, it will eventually flatten out, right? And maybe you're wondering, but sir, I thought you said the solar system is not flat. Flat. I mean, I thought you said that the solar system is, flat at the middle, and then you have the Kuiper belt, and then the Oort cloud, which is a sphere, so it's not flattened out. So that's just what we're saying. What we're saying is, over time it will flatten out, but obviously this takes time. So, what you can say is, if the solar system were to survive for another 10 billion years, probably the Oort cloud would flatten out, but uh, but the sun would probably die by that time. But the point is the fact that majority, because the Oort clouds are so in the edges of the solar system already, but majority of the momentum, majority of the mass in the solar system, which is obviously in the planets and in the sun, are flattened out. Okay, so that's the idea. Okay, so it flattens out into this term, a protoplanetary disk. So a protoplanetary disk is a disk, it's like a flat one where planets are created. And why do we believe that protoplanetary disks are like this? Well, again, logic would tell us that, okay, if the solar system came from a nebula, and if we look at the skies right now, we see other nebulae in the sky. So maybe some of these nebulae that we can see also contains the early stages of planet formation. And so all we need to do is, point our cameras to the sky and look for those things. And guess what? That's what we see. So if we look at this picture that I'm pulling up now, these are protoplanetary disks that we have found so far. So these are not, I know they look like drawings or computer drawings, but these are real images, obviously enhanced, but these are real images captured from ground-based instruments and maybe some space-based instruments. So, for example, here are XJ161. So you see that disk? You see that disk? This is a disk. That's a disk. But if you notice, it's a disk, but it's still made up of dust. So, in this case, the blob of particles has flattened out. So now it's a disk. But the planets have not formed yet. Okay? The planets have not formed yet. But that proves you that, again, when you have a shapeless blob of nebula and you started rotating it, it will flatten out. Well, there's another analogy, although this is kind of really full of holes, but kind of like why pizza makers like to rotate the dough, because rotation of the dough kind of flattens out. Although the flattening out is not really because of the same forces as what flattens out the blob of particles in space, because there's gravity and it becomes more complicated. But kind of the same thing. When it rotates, it flattens out over time. So here we see a stage where it flattens out, but the planets and the sun have not, or the sun in this particular systems have not formed yet. But that will happen next, because I'm sorry, I realized I was not showing you the screen. So let us repeat. So these are the protoplanetary disks. Again, they have flattened out, but the sun and the stars, or the star and the planets, have not formed yet. But that will happen next time, because number 4, when it flattens out, most of the cloud condensed at the center, making it very hot. So if you notice here, most of the picture, you notice that the center seems to be brightest. Obviously, there are some exceptions like this one, but most of them at the center, it's brightest. That's because the center becomes the hottest part, because when it rotates, most of the particles kind of drift towards each other, towards the center, And why is that? Why is that? Well, it's because of gravity. Remember, gravity pulls you to the center of things. So again, when we say gravity is a force that pulls downwards, again, that's not kind of true, because when you're here, downwards means that. When you are here in the world, downwards means this. Meaning, downwards really means to the center of the earth. Right? So if in the earth, everything that falls down kind of goes to the center, so in the solar system, in the early solar system at least, then all of those gravity will kind of conglomerate also at the center. So the center has a lot of mass, right? Has a lot of mass. And in fact, that is true even up to now. If you compare the masses of the planets compared to the mass of the sun, there is a wide disparity. The sun is so much massive than all the planets combined, because again, math predicts that most of the particles will condense at the center, right? And then as the temperature of the center rose to millions of degrees, nuclear fusion was initiated and the newborn sun ignited. Okay? So this is kind of like, again, related to what we have been studying. When you compress something so much, right, it becomes more and more solid, and it becomes hotter and hotter and hotter and hotter. That's why the center of the earth, the core of the earth, is very hot. But if you make it very, 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 very hot, it would actually ignite nuclear fusion. It would actually ignite nuclear fusion. And if you remember your grade 9, nuclear fusion is what makes the stars burn, quote unquote, because they're not really burning. It's not combustion, but they are consuming the hydrogen, fusing them to become helium, fusing helium and helium to make it boron or whatever, until it becomes oxygen, right? You know this. I remember Mom Cabaron, I don't know about last year, but I remember Mom Cabaron discussing about main sequence of stars. Main sequence, like how stars fuse hydrogen to make it helium, and helium to make helium and hydrogen to make it lithium, or two heliums to make it boron, because of course hydrogen is 1, helium is 2, lithium is 3, boron is 4. So when you have 2 and 2, helium and helium, becomes boron. When you have 2 and 1, helium and hydrogen, it becomes lithium. And so that's how you build up the elements of the periodic table. From helium, from hydrogen it becomes helium, it becomes boron, oxygen, until it becomes iron. Okay, but let's read what the evidence posted here is. So here, real pictures of protoplanetary disk taken by Hubble reveal that the temperature at the centers is hottest than the other areas of the disk. So again, what could be a greater evidence than this? We see this. Let me remind you, we see this out there. So if we see this out there in the nebula, and we are theorizing that our solar system also came from a nebula, then what is happening there right now would have been what was happening in our own nebula to form our solar system. Okay? And then here, this one. Experiments in magnetic confinement fusion reactors show that high pressures and temperatures lead to fusion, nuclear fusion, reaction of light elements like hydrogen. Okay? So, we actually have done this in experiments. So, if I again pull up another picture here, this is a picture of a tokamak. A tokamak is a device that kind of confines hydrogen particles together, or not really hydrogen, but particles together, so that they become so compressed. And when they compress, it ignites and becomes fusion, and triggers fusion, and we can make our own star. We can make our own star, kind of like if you watch like Spider-Man 2, Tobey Maguire, his enemy was Doc Ock, and Doc Ock was trying to create artificial star through fusion. That's the idea. You fuse materials together, probably lighter elements like helium, and then what happens is it would ignite and become and would trigger fusion. Again, you would have a star. But again, the problem here is so sir, is this a technology that we have now? Yes, we have tokamaks, and we know that fusion is possible. We know that when we fuse something, when you compress something so much, it ignites and becomes fusion, and triggers the process of fusion. So sir, if that's the case, we can make our own star here on Earth. Yes. So in that case, we have infinite amounts of energy. No, because the idea here is you have to remember it's not about whether you can get energy out of it. It's about is it profitable, right? So if I were to tell you I have a 100 peso bill and I have 100 peso bill, buy it, and I will sell my 100 peso bill for 150 pesos. You would say you're crazy. Who would buy a 100 peso bill for a price of 150? Right? So it's about the cost and what you get out of it. So right now, tokamaks work. Okay? We can make fusion. The problem is the amount of energy we input is so high compared to the amount of energy that we get out of it. So what happens is, to operate this tokamaks, we have to create like strong magnetic fields, right? So if we click here, this requires a magnetic field, right? And that magnetic field is created by electricity. So we have to supply electricity to create these magnetic fields to fuse the thing to create fusion. And when fusion happens, we get energy out of it. The problem is, right now, the amount of energy that we input is so high compared to the energy that we get that it's really not feasible, right? It's kind of like buying 100 pesos for the price of 150. It doesn't make sense. You don't spend more energy just to get some energy out. And by the way, this is also one of the things in science also, like there's also economics built into it, because a lot of students always point out to the fact that, you know, a Filipino was able to discover that water is H2O. You can split water into H2 and O2, right? And then H2 is a fuel. H2 is flammable. O2 is also flammable. In fact, it's one of the requirements of combustion. You need oxygen to burn things. So therefore, we just split water and then we use the fuel to power our vehicles. And then a Filipino discovered this, that water can be used to kind of make a vehicle just from the hydrogen fuel. Yes, I understand. The concept is sound. The concept is feasible. The problem is, how do you split water? You split water by using electricity. And that's the problem there. Because the amount of electricity that you input, let's say 30 joules, you have to input energy somehow to break that water into hydrogen and oxygen. And then when you burn this, you only get, say, 25 joules. Obviously, I'm making up these numbers, but the point is, the problem is this. It's not about the feasibility of the concept. It's about the amount of energy. If you spend too much energy to break water into H2 and O2, just so that you would burn it to get a lower amount of energy, then why not just use this energy to create motion? Why not use the electricity directly to create motions of cars? This is what Tesla is doing now. Remember, in Tesla, you have electric vehicles, and electric vehicles use electricity stored in their batteries to make it move. So see, there's a lot of fake news in the internet saying that, you know, a Filipino discovered how to break water into one and can power vehicles, but you know, the US has been suppressing this technology. The big oil companies has been suppressing technology. No, when you learn science, you would learn that, you know, the amount of energy to break apart a water molecule into these two components is big compared to the energy that you get out of it, that it's not worth it. Okay, it's not worth it. Well, you could say that again. What if we get the electricity from the sun, sir, so that we don't have to spend energy? Again, the same thing. If you spend sun's energy to break this up and get this energy, why not just use directly the energy from the sun to power your motor? You see? So it's like that. So obviously, there are concepts like that in science that you have to know. So again, um, why do we believe that why do we believe that when the cloud condenses at the center, it becomes very hot, and then it triggers nuclear fusion? That's why the star kind of starts to ignite. Well, because again, we can do that in our laboratory. We have tokamaks that can do that. But again, right now it's not feasible because the amount of energy that we input to these things are so large compared to the amount of energy that we can get out of it. But the point is that now takes care of the idea of how we create a star from a blob of nebula, from a blob of dust particles. Okay? And then 6, the remaining dust of the disk clump together because of static charge and form planetesimals. Okay, so here we are saying that while the center of the solar system, so now we are forming a protoplanetary disk, right? Protoplanetary disk, and most of the materials are here, and this ignites because of nuclear fusion and creates the star. How about the rest of the particles here? So the rest of the particles here, the rest of the particles here would actually clump together and form planetesimals. So they would clump together. And why would they clump together, sir? Why would they kind of stick together? Well, it's because of static electricity, right? Like if you have a comb, plastic comb, you rub it with your hair, then all of a sudden it will be able to attract small pieces of particles because of static electricity. Obviously, you have to know about magnetism, electricity to understand that, and I don't have time. But the point is, there's static electricity, and if you're, in case you're wondering, this is the reason why in your homes, if you don't clean often, you have what we call dust bunnies. You notice those dust bunnies when you have dust particles clumping together to form like a string of dust particles. That's what we call dust bunnies. That's because of static electricity, right? So they clump together because of static electricity, and then we move on to the next one. Some planetesimals collided with each other and formed bigger and bigger bodies until they became protoplanets. So it's like, okay, a dust clump of dust is formed here, clump of dust is formed here, clump of dust is formed here, and because of gravity, those dust particles would attract each other and they will join forces. So from dust particles, you have clumps of dust, then clumps of dust become planetesimals, then these planetesimals join together and form protoplanets. Okay, and I have here a simulation that does just that. Um, Let me see where that is. I think it is this one. No, this is just a demonstration of static electricity, right? So see, those dust particles are attracted by this one because that particle is charged. In this case, when you rub things together, it becomes charged, that it actually attracts other things to it, right? So so notice what he did here. What he did here first was rub things together. Okay, let me. So he was rubbing that with another thing, and then that causes static electricity to build up, and you can make attractions, right? And that's the idea there. So when these particles kind of rotated in the dust in the protoplanetary disk, maybe some of them rub off each other, forming those, building the static charge, and these static charge cause them to clump together and form dust bunnies. And I have here another simulation which gives you this one. And remember, protoplanets that form from here will always be as spheres. And why is that a sphere? because again of gravity. That's how gravity works. So this is a simulation of a lot of particles, and by the way, this is done in a computer. But what it's doing is we are it's inputting the equations of gravity in each of those particles, and you can do that in a computer, and so that we can see kind of what really happens. So I'll just fast forward this one. So you see, you have clumps of particles, and those clumps of particles, the clumps of the clumps, tend to clump together, if you know what I mean. So the so it means that it becomes bigger and bigger and bigger, like that. Maybe that's not so clear, so let's find another simulation. This is probably better, and this is also more reliable because this is created by a group of scientists. So this is really a study, not a one. I'm sorry. Here. That's a protoplanetary disk, right? That it's creating. This is from Princeton University, I see. So credits to them for this. So if you zoom into the disk itself, so this is the part of the disk, right? So part of the disk, you can start to see that there are clumps of materials. There are structures of materials that are created, namely clumps. So here, okay, and those become protoplanets. Those become planetesimals, and the planetesimals collide to become protoplanets, and the protoplanets collide and become planets. Okay, so that's the idea. By the way, that's also in YouTube, so you can search for that. There was this. I need. Okay, so that's the idea. So now when you look at the picture, now you can see, okay, sir, I see a bright light here. Sorry, it's not showing the screen. I see a bright light here, so that would probably be the star that started to ignite. But see, I see a dark band around. And also I see a dark band around. Why is this dark? So the idea is that part is dark because it has no dust in it. And why is that part having no dust? That's probably because a planet has been formed there. And as it revolves around the star, the young star, it sweeps up the material. That's why that area is empty. Okay, so let me point that out to you here. So you have a dark kind of circular pattern here. This dark part here, that's a place where a planet would have been formed, and that's why it's dark right now, because it picks up all the particles that are in there. And also here, there's another planet that is being formed. So here, this line here that is kind of dark, that means there's a planet there that's sweeping up the materials, the particles, the dust there. That's why it's not lighted, because what is illuminating here are the dust particles. The dust particles are reflecting light. But that is dark because something is picking the particles up. So here you see a protoplanetary disk complete with a star at the center and what would become planets. And you see these bands of dark patches, these dark patches, these dark circular things. Those are the pathways of planets. Okay, so here you have, again, let's recap, because I want to stop the video now and I want to make another video because this has become too lengthy. But the idea is you have a nebular cloud. Again, supernova triggered it to rotate. Because of rotation, math predicts that it will flatten out over time, forming a disk. And when it flattens out over time, another effect is, aside from flattening out, is most of the material will come at the center, will be compressed at the center. And then when most of the materials are compressed at the center, compression becomes the temperature so high, the pressure so high that it ignites and triggers fusion, igniting the star. And then the rest of the particles of the disk will continue to rotate, but as they rotate, they rub with each other. They form static electricity. Static electricity causes them to clump. The clump will clump, and the clumps of clumps will clump together to form bigger and bigger and bigger structures. So you have dust particles forming clumps of dust, forming planetesimals, planetesimals forming protoplanets, and eventually those protoplanets would create planets. But that is it for this video. We will continue this in the next video because this has become lengthy already.